Welcome to Halteres Presents, a brand agnostic interview podcast that seeks to objectively highlight the happenings within the world of diagnostics. And now, your hosts, Thayer and Mickey Urdea.
Hello, and welcome to Halteres Presents. This is Rich Thayer, Managing Partner at Halteres Associates.
And this is Mickey Urdea, Founding Partner at Halteres. And now we're going to go into part 2 of our discussion with Paul Davis. It's a fascinating discussion about all of the innovations which have occurred over the course of the last several decades in the consumer diagnostics industry, particularly with regard to improvements in the technology associated with lateral flow assays. He and his team have learned a great deal over the last many years, and he's going to actually tell us about how best to think about the science behind lateral flow assays and create even better ones than we have today.
Lateral flow technologies have been around now for nearly 50 years. It's exciting to hear about the new innovations underway today in the lab.
If anybody skipped part 1, we recommend you go back and listen to the first episode because you'll find it fascinating as well. And now, part 2 of our interview with Paul Davis.
Thank you, Paul. Thinking beyond pregnancy testing, LFAs are in fact being introduced into many branches of medicine, both in high-income countries and in low and middle-income countries, and at many different levels of healthcare. Looking back, how widely have LFAs been adopted? What are some of the greatest contributions of LFA tests, and how do those tests perform today versus the big lab tests? And if I might add, looking forward, what's exciting you? What's in the pipeline? What new diagnostic applications are in the innovation pipeline for LFAs?
That's a lovely open question. As far as I can see, lateral flow tests have made great contributions in malaria and also in other tropical infectious disease areas. They're making great contributions in HIV. They're beginning to do so in TB. But in all of these cases, I think their biggest contribution is yet to come because we've got to wrestle the prices down without compromising performance, and those are tasks that still have to be done, particularly in malaria, where the price competition has made it so that the cheapest tests are being distributed and sold, but they're not the best tests. And so we do have problems to overcome, but nonetheless, they're already making great inroads in these areas. So influenza testing, that's all benefited enormously from the presence of lateral flow tests. Dengue, sexually transmitted diseases. And if anybody wants to get a feeling for how widely it's being spread, then I would suggest they go onto the Quidel website, where there's a very impressive array of lateral flow tests for all sorts of diseases. It's difficult to know how many are being sold and to what extent they've actually had an impact on the control of the disease, providing better medicine and so on. But that's only going to improve as the tests get better. I think there are some really exciting tests to come. And we are starting to work with an Oxford-based company called NeuroBio, founded by Baroness Susan Greenfield. And she has come up with a peptide called T14, which is released from acetylcholinesterase. And T14 is absolutely critical in the development of the brain in embryology and early life. It actually drives the maturation and differentiation of the brain. But she has found very convincing evidence that if that T14 is unleashed in adult life, it then works as a toxin because the brain is already where it should be. It's already developed. And if T14 is allowed back into the scene, which it can be through disease or through damage and other factors that aren't yet understood, it can be a driver of toxicity in the brain that is likely to lead to Alzheimer's disease. And it appears that measuring T14 in nasal secretions is a good way to determine whether somebody in their 30s or 40s or even 50s is actually developing a problem that can take them into Alzheimer's disease. So measuring T14 in the population is going to be a huge opportunity as that work progresses. And so we're very keen to find ways in which we can utilize our experience of nasal secretion going into lateral flow tests to look for T14. And that's work that we're just beginning. That, I think, is hugely exciting. It's early days, and the T14 hypothesis is looking very strong, and it still has to be confirmed. But we're right there, thinking, believing that this is the way forward. And that's going to be selling vast numbers of tests, making it usable and frequently, just like the pregnancy test, but for anybody to make sure, maybe on an annual basis, that their T14 levels are not too high. So that's another one that I think is going to become important. The most exciting thing about the T14 project is that there is a treatment that comes along with it. And NeuroBio, under Susan Greenfield's leadership, has come up with an antagonist. It's actually a cyclized version of the T14 peptide. And wonderfully, it does the job of blocking the damage that T14 would do. So this diagnostic will have the benefit of being made available at the same time as an effective remedy is made available too. So if somebody finds their T14 is high, what do? They take the T14 antagonist, and they can be confident that while they're taking that, they will be free from developing into a state of dementia through Alzheimer's disease. That's pretty exciting. If anyone's interested in this Alzheimer's project, then I strongly urge you to visit the NeuroBio website. It's NeuroBio, neuro-bio.com. And there's a very simple and fascinating video which explains the concepts. And there's lots of published papers that are listed there and accessible from there, which would allow you to follow up the science that's gone on already. Well worth a visit. As I was saying a few moments ago, there's work to be done to prove the theory, and it's very strong and exciting to be part of it. And as we go forward, the diagnostic test will help with the trials that will be coming through. We also have our COPD exacerbation test, and that's a multiplex test that our first publication for that is coming up, and it's measuring 5 biomarkers in urine that have been shown in the initial tests that we've done to be able to tell people with COPD that they have an exacerbation coming. I maybe need to briefly mention that with COPD sufferers, they have this lung condition. It's compromising their life, and they're living with it. But the problem is that exacerbations occur, and exacerbations are frightening. They're horrible, and they can cause more damage. So if people can be given warning that an exacerbation is on the way, they can start their medication early. And the new drugs that have been developed to help with COVID are almost certainly going to help with COPD, but knowing when to take them. And so this product is doing extremely well in its early trials at delivering warning of around about 7 days. And the really unusual thing about it is that it's based on urinary biomarkers. So why would urinary biomarkers be important in a lung condition? It's because the lung is so highly perfused. When the inflammatory process starts, you get inflammatory mediators leaking into the blood. Some of them are enzymes, proteases. That gets into another highly perfused organ, the kidney. Starts off a little bit of transmission, and then the floodgates open, and these biomarkers coming from the lung can be picked up in the urine. So the results for the 5 markers are then put through 3 algorithms using AI. The first one is the biomarker monitoring algorithm, and then the exacerbation monitoring algorithm, and then the decision rules algorithm. And as a result of that, we get this index coming through that can be very highly predictive. We're really excited by the results we're getting, and the first publication is going through. And again, we're working with physicians, specialist physicians in the pulmonary area, to make sure that what we're doing is on track. That's the technology where there's lateral flows in the home with a reader, and with frequent testing. So there's just two examples.
Yeah, that's fascinating, Paul. There's been quite a call in a similar circumstance for severe asthmatics, an early warning test, if you will, for pending
Yes.
asthma, especially around children, perhaps, headed to school, etc. Have you given any thoughts to applying the same type of approach to asthma?
Yes, we have. And we've gone along to asthma meetings and met the asthma societies and so on. And we think there's scope there. We also think there's scope for cystic fibrosis, which has similar problems. And in terms of products in the pipeline, we've got so that one is called Head Start, and I'd like to see that eventually in asthma and in the cystic fibrosis, but you can't take on too many things at once. And then there's Right Start, which is to use blood biomarkers this time in COPD to determine whether it's a viral or a bacterial exacerbation that's coming. And so Right Start means you start the right medication at the right time. And we also have a sepsis product that's in a fairly advanced stage, and Utriplex, which is a UTI test. So those are some of the things that we're doing that we think are really exciting. And our challenge is to get the right timing to work with partners that can bring what we can't, because it's naive to think that a company that's focused on innovation and the types of things that we do with diagnostics could deliver everything we need for this sort of bigger application involving medication in a situation like COPD in a chronic disease. We hope eventually, and not before too long, that we can make low-cost versions that can be used in LMICs.
Wow, that's a great ambition.
Yeah. In answer, Rich, to your question about how lateral flow tests compare to laboratory tests, then at this stage, lateral flow tests are nowhere near as precise as laboratory tests. And that really takes us into the whole point about use cases. So for any lateral flow test, as for any diagnostic test, you need to be very clear about the use case. And the use case of semi-quantitative, I'm not sure that that's a valid statement to make, so if it's either quantitative or it's not, but let's say some there that's nearly quantitative, really has a very great usefulness in the right situation. So if you're in pregnancy test, of course, is the perfect example. You don't need precise quantification. You just need to know whether HCG hormone is present in the urine above a certain level. And when it comes to things like detecting whether an individual is suffering from a malaria infection, you don't need precise numbers. So lateral flow tests need to be used where it's not necessary to have precise numbers. But I do believe this will change, and I'm quite enthusiastic about the idea that, for example, the electronic lateral flow that we're working on, especially when we get new membrane material that's more precise than nitrocellulose, I believe that the quantification aspects of lateral flow will improve markedly. So they'll probably never be as precise as a laboratory test, but they might be pretty good. And their usefulness will extend in situations where numbers are important.
Are there any examples, though, where perhaps some LFA tests are getting close to laboratory test quality of results?
I think that's true, that they can be. So, for example, if you're looking at the specificity and sensitivity or predictive value, then you can get very close, because on those things, you're looking at the ability of the test to define a diagnosis. And so they would be maybe just as good. even if they haven't got the analytical precision. If you start to look at analytical precision, then working with a laboratory machine, an architect or one of these sophisticated tests, then the analytical precision would be less in a lateral flow. But that doesn't stop them being highly effective in terms of diagnostic efficiency.
That makes sense. Thank you.
So, Paul, LFA technology is generally considered to be in the mature stage of its life cycle. For most mature products or technologies, the emphasis is on cost reduction, standardization, increasing efficiencies, and coping with widespread competition. Do you think we can expect to see any radical new LFA derivations emerge? And if so, what do you think they will be, and when are they likely to appear?
Yes, I think you can. There's some that are present with us now that are going to be seen as really quite significant developments in terms of personal testing. So I would like to encourage people to have a look online at a website called COVID-Go, COVID-Go.com. And this is a technology that was developed in Mologic /GADX, and we call it the egg timer format, as you will see if you go to that website. Basically, it's a very simplified personal testing system in which you just have to take the swab, pop it into this cylindrical tube standing upright, push it in, click it, swing it back and forth, and then turn it upside down. And so the very simple thing is swab, click, shake and flip. And this was supported by Radix because of its extreme simplicity. And it's now got EUA approval. And Radix is further supporting it with GADX so that it's possible to make it even simpler for people that are blind or with other disabilities, so that they can do a test like this, which would be impossible if they were having to use a normal lateral flow strip. That's quite an exciting development. It's basically still same visual lateral flow. We also have some longer term innovations emerging from the work of the Center for Advanced Rapid Diagnostics. These are longer term because they're much more fundamental innovations using completely new technologies.
Yes, Paul, I wanted to ask you more about that, some of the work that you've done in setting up the Center for Advanced Rapid Diagnostics with Mologic. We'd like to explore that a little bit more with you. So what were some of the overarching objectives of CARD? And did this permit you and your team to explore some of the shortcomings of LFA technologies and how to improve LFAs?
Yes. As we have been aware for many years, lateral flows can be developed and manufactured all over the world, often to very high standards of quality. This was even more apparent in the COVID pandemic, when we could also see untrained people all over the world being able to use the tests that were being made in the home or in the workplace. So by any standards, lateral flow is actually a robust, widely used technique, and it has become a pretty standardized piece of industry. Away from industry, there are many research groups in universities busy developing improvements and derivatives of lateral flow immunoassay, publishing them in research papers and patents, and including Mologic and GADX. But the CARD came about to rather take a different view. The CARD primary question in 2017, when we started with funding from the Bill and Melinda Gates Foundation, it had as its overarching objectives to dig deeper into the science behind lateral flow technology, with a view to being able to make tests simpler and cheaper, and also tests that were more sophisticated and could bring more advanced diagnostics to LMICs. And so the approach that we took was really to get into the underlying science and ask basic questions. That turns out to be a very rewarding thing to do, and we were provided with sufficient resources to be able to set up a a dedicated laboratory with advanced equipment in, and we were able to get on with wrestling with questions of how was it working, what were the areas that it could improve in, what were the things that couldn't be improved, was there any basis for believing that there was a long-term future for lateral flow, or would it be replaced by other technologies? So right from 2017 onwards, we have been working on these areas. The particular questions that I should point you to are, what are realistic limits and opportunities that go in terms of the sensitivity that's achievable with a visual lateral flow? What is the scope of the assay type that could be carried out on lateral flow test strips? Also, what kind of additional applications might be possible? How can we do something about the cost of lateral flow tests? What about manufacture and the materials that could be used in them? How to make them even more simple and user-friendly? And all of this leading to that basic question of, is there a wider future for lateral flow immunoassay? One of the things that we started with early on was to see how far we could push a visual lateral flow assay using the P24 protein from HIV. It turns out that P24 protein is actually highly immunogenic, and we were able to get some very interesting antibodies against P24. And there were some really interesting features about those, because it turns out that we were getting augmented affinity, and that if we let the antibody bind the P24 in the right order, then one of the antibodies will bring about a change in configuration of the antigen, which would make it even more tightly bound by the second antibody. That was our augmented affinity. And with this, and with a different kind of particle, we were able to be confident about detecting P24 in blood serum at the level of 1 picogram per mil. Excited by this, we moved on to LDH from malaria, lactate dehydrogenase, and it turns out that lactate dehydrogenase isn't as immunogenic as P24. Perhaps not surprising, since all animals have lactate dehydrogenase in as one of their important housekeeping enzymes, and so it's quite highly conserved. So we were never able to get antibodies that appeared on our affinity contour map with the same levels of affinity, the same on rates and low off rates, high on rates and low off rates. Those are things that are absolutely essential to get high affinity. And it got even more difficult when you start to look at trying to get high affinity antibodies that can distinguish between Plasmodium falciparum, LDH, and Plasmodium vivax, LDH. And that it involves such a small difference in the amino acid sequence of those two proteins that there was never a really large surface area for the antibodies to get hold of. So sure, we could do it, but we were probably getting on for 1,000 times less sensitive. Fortunately, that's sufficient for the use case. We talked about use case earlier. In the use case for this, then an assay around about 1 nanogram per mil is adequate for the purpose of doing the diagnosis that's needed for malaria. But it brought home this really powerful understanding. So as part of the digging deeper, we were able to dig deeper into that and start to develop our 5 pillars of wisdom that come from the work of the card.
5 pillars of wisdom. You must be a T.E. Lawrence fan.
Yes, exactly. You can see where I got it from.
Yes.
So the work of the card, I need to explain this really, that there was scientific understanding coming from that, on which we were able to build new plans and new opportunities to bring assay innovations, as well as to address different biomarkers. And there were also specific developments that we see arising from the card work, which are to do with new technology. So new scientific understanding and a rising new technology coming from it. So the particular device type outputs, which are built on the scientific work that we were doing, which was particularly strongly involved in the affinity, the strength of binding of antibodies to antigens, was to build a complete understanding of the factors that determine lateral flow performance and manufacture, to work with the basic visual lateral flow. Here we're asking the question of how far can we push lateral flow in its traditional form, forming a visual line that would be seen by eye or maybe photographed, extend the usefulness of the visual lateral flow, and build it into a pragmatic mathematical model that would help people to be very confident about what they're likely to achieve when they address a particular biomarker, which could then be assessed for how antigenic it is, or what kind of affinity of antibodies can be produced. How is that assay going to look without having to waste ages, never achieving what would be required? That's quite an important thing. So that's about being more confident, more understanding about particular assays. The second output was to expand the scope. And in that situation, then the first one to come through is the NATOS, which stands for Nucleic Acid Amplification Test on a Strip. And there the card is working at this time, is still working with the Global Health Labs on a very important project to get a slick, self-contained, easy to use nucleic acid test on a strip. That's a step change in nucleic acid testing and making it available for at the point of care and for low resource settings. Everything will be there on the strip, including the power that's needed, and I've been watching that with great excitement as it moves forward. And when I indulge in imagineering, where, to quote a well-known phrase, I let my imagination soar into the air, I think to myself, what else would I like people to be able to do in the resource-poor parts of the world? And that would be for them to be able to do tests on lymphocytes, where there isn't a lab that does cell culture, where there aren't the resources to do that. And then I think, well, if we had a really suitable test strip, we could actually do the lymphocyte culturing in the strip. And I have this pipe dream in which I can see all the elements that we need from the understanding we've got from the card, and which I believe it will be possible with the right skills, the right project leadership, and the right funding. It will be possible to make a test where we can put white cells in the strip, culture it, and have the antibodies that we need to read the cytokine profile actually there present in with the cultured lymphocyte. That's a pipe dream. That's the sort of imagineering that we like to do coming out of the card. NATOS isn't a pipe dream. NATOS is underway and going well. I could now like to just take you to the third outcome, which is to go beyond the limits of conventional lateral flow immunoassay performance with supreme ease of use, connectivity, and performance. And that's Adelphia, which stands for Autonomous Device Electronic Lateral Flow Immunoassay. It's a digital lateral flow platform with autonomous operation. You just put the sample in, followed by a chase fluid, and the thing takes care of itself, and it ends up as a digital readout. Why do we want to do Adelphia? The project's running. It's moved into feasibility. We've got all the basic parts working. And what is it we expect it to do? Well, to increase analytical sensitivity when needed, because there's a dual layer amplification, improve accuracy and reproducibility, transform into a truly quantitative test, optimize multiplexing on single strips, work as an autonomous device with walk-away test method after adding sample and chase fluid, streamline and simplify connectivity for ease of use and direct integration into digital health systems, maximize the manufacturability at scale, minimize user errors and avoid interference by users because they won't ever see the result. It'll just be going into an electronic station. It will just be into a smartphone, a smart device, and harness and augment the robust advantages of lateral flow in a different way. Because whatever else you say about lateral flow, it is robust. Great thing about it is that it allowed immunoassay to escape from the lab. And because of the way it runs in a lateral flow, in a sequential way with layers of fluidics, it actually achieves a multi-step immunoassay in a single step. And it was the first embodiment of it was the clear blue one step. And that's what it was. And that's what it is. And it's such a useful platform on which to build these things.
I think there's a very exciting advancement because it takes advantage of the fact that you can put all these things into a very small disposable device that doesn't require an additional instrument to read and get the level of precision that is possible with an instrument. We've seen all these opportunities to bring in fluorescent assays or chemiluminescent assays, but the downside is the additional instrument, which makes it difficult to use in all the places you would like to use such a LFA test.
Thank you. Okay, so some of the enabling innovations which are already achieved and working is that we have a really novel feature of substrate generation is in situ, so that the electrochemistry system makes its own substrate. So nobody has to add substrate to get the signal to start working. So we can use enzymatic signaling or a catalytic nanoparticle signaling without user intervention because of that. We've got near field communication so that all you have to do is let the phone speak to the device. And the electronic signal transduction is taking place within the test line in the strip. We're converting the test line into being an electrochemical transducer that generates charge in proportion to the amount of analyte that's bound there. And it uses platform single-use printed saline batteries. And I think this is really, I think the term is cool, that the chase buffer does two things. One is it's a chase buffer that pushes along the assay into the immunoassay strip. The other is that same material, an excess of it, you add a little bit of, goes into the battery. And as it goes into the battery, the sodium chloride part of it actually fires up the battery. So it's one less component, one less step, and it all wakes up when that happens. And the end result is that we are able to use standard manufacturing capacity and processes. There's a really great simplicity of operation and reliability, sensitivity, connectivity. And the final piece of icing on the top is that we now have structured approaches that will allow us to be able to have multiplexing, very neat, no crosstalk multiplexing, which we think is going to be a big improvement. And to keep the cost down, it will use an external microcontroller that will plug in rather like a glucose test. So we think all of these things are going to make a big difference when it comes together. So as I said, we've reached feasibility. We've got the test working, but there's still quite a bit of work to do. And what we really need at this point is a partnership with a company that can add to our innovations and help us to develop the right kind of product for the right kind of market. Because in the end, we'll be coming back to the user case, and we want the right user case so that we develop this such that the technology takes us into the right kind of system that is ready to be appropriate in the way it's to be used and by whom.
I mean, so many people are interested in having multiplexed assays of one kind or another for LFAs, but it always requires a reader sitting next to it. And in a situation like this, you wouldn't have to have that, which is very attractive.
Yeah.
I want to ask you a little bit about reagents and how one gets the appropriate reagent. Traditionally, what's happened, as you well know, is that people go and find every antibody available for a particular application they have in mind and hope that they can screen something that will have the appropriate performance, which is more luck than it is design. Whereas some of these other reagents, like aptamers, it's possible to actually select for the binding. Whether you can get it or not is another matter. But how does one take then practically the lessons you're learning about the appropriate design and efficiently get to reagents that you can use that will have predictable performance?
That's a very good question. And it's highlighting the fact that we can know what we want, but not be able to yet necessarily make it to order. So this is where the deep dive that we took can be helpful. The deep dive into the science underneath what's going on and looking at the antibody technology. And so one of the things is that you need to look at the kind of, the species of antibody that you want. So if you're going to work from an immunized library, for example, then if you choose rabbit or mouse or sheep or goats, then you need to bear in mind the way they mature and the antibody, the way they structure it. So you've got things like the VDJ part of the construction of an antibody. And those things can have a big impact on how an antibody is arranged. We actually produced a roadmap of how you can look at antibody production. And that roadmap allows or takes you into the different types of species that you can use. But you can also do other things like designing an epitope so that you make the most of the epitope that you think is available. So the way I would do it is I'd first see what the epitope availability is in the antibody, in the antigen that I want to detect. I then think about the best way to prime that into the animal that's going to be responding, or to the cell system if you're going to do it in a test tube, and then go through the process of either B cell cloning or putting the genes of the antibodies into a phage library. We did a study in which we wanted to make antibodies against hemoglobin A1C, but instead of making antibodies against the traditional N-terminal valine, which reacts with glucose to give you fructosamine on the end of the N-terminal group, and you can define the linear amino acid sequence that that's attached to. But we knew that there were other lysine residues that were exposed and which would also become reactive with the glucose to give you a fructosamine attached. And we then used the epitope-directed immunization in the way that I've described using sheep. And then we did phage display, and with appropriate selection techniques, we were able to find the antibody that doesn't bind the N-terminal valine, but binds the other sites based upon lysine. And there it depends on the conformation of the protein. We believe that this works with a different rate of glycation, which will potentially tell us more about get more information out of the hemoglobin A1C test. And that's an example of how you can use a combination of choosing the right animal host. And there's some companies out there that can do some wonderful work, and we've had experience of working with them. So choosing your company, choosing the species, and then doing phage display to come up with the right kind of antibody. There's still some screening. You're still not in total control. The only way you could be in total control would be if or when computational approaches would allow you to synthesize the antibody de novo. But at the moment, that wouldn't be cost effective. So one of the worst things to me when we do contract research or contract development is when somebody comes and says, we've got antibodies to this antigen, please build it into a lateral flow. And I think, oh no. It's highly unlikely that they will be the antibodies that we really want. We'd much rather start by making the antibodies And one of the things to consider is antibodies are such an important part of a lateral flow. They're worth investing in, and it's worth spending time to get the very best.
Yeah,
Definitely.
makes a lot of sense.
Paul, in the beginning of this interview, you talked a lot about your days at Unilever and the innovation process and fostering creativity, et cetera. What have you learned about innovation within the context of commercial organizations? How can innovation be promoted or encouraged and harnessed into effective products? And what advice would you have for inventors and our innovators?
Yeah, this is a subject on which I have some quite passionate feelings. As I've emphasized several times, I think, in this podcast, I'm very interested in the dynamics of teamwork, because teamwork is so important. Teamwork is what makes it possible to achieve great things, which individuals can't do on their own, least of all me. And when I was in Unilever, going back now over 20 years, I was sometimes troubled by the fact that although I get on well with most people, there were one or two people, usually people in authority, who I had certain problems with. And I was frustrated that very often people who I respected amongst my peers were not being given the credit and the encouragement to be creative. And so when I was made a creativity mentor, which was a completely new position, and I hadn't really got much idea what to do, I was lucky enough to come across the Curtin Adapter Innovator Spectrum, which is a kind of team-working tool. It's a way of making people understand their creativity, making them understand the way they solve problems and work. And this was one of the sort of transformational moments for me, when it really made such perfect sense, and it's just such a simple concept. And it's all about people having original ideas. All human beings have original ideas. It's part of being human. And problem solving, it's part of being human. But people differ in their preferred style of idea generation. And this is, of course, my take on the Curtin spectrum, Kirton, I need to emphasize, not curtain as in window dressing. With his spectrum, it's possible to understand the different ways that people like to work. And so he drew out this spectrum and said that there are people who he calls adapters, who like to adapt a situation to solve a problem according to preset rules. So, for example, an airline pilot must be an adapter because he has rules that he has to follow. He has to solve problems, sometimes life and death problems, sometimes dramatic problems, but he has to solve them and likes to solve them within a pre-given framework. At the other end, you have the innovators, and they're really sort of rampant inventors. These are people that don't like and can't work in rules. If there was a problem, they'd rather reinvent the rules around it rather than work within a framework. And these people are the sort of drivers of invention. And examples might be, for example, a sculptor who's had a lump of stone in front of him or her, and they're going to create a sculpture, and they don't know what it's going to look like at the end until they've done it. They might have an idea what it will be like. Painters or people like Einstein, who thought differently about things and rejected all the physics that were known at the time and looked at the world in a completely different way. And so these two extremes highlight the continuum, because people fit somewhere within that continuum. And there's a fantastically insightful set of 20 questions that allows you to understand where you fit. But most people immediately know where they fit. Bank manager will be proud to be an adapter. He's not going to invent new rules or find new ways to sort out your money. He'll work within the given provisions. But somebody who's asked to reinvent lateral flow or come up with a new pregnancy test can't work within the rules. They've got to be creative. They've got to do things differently. Although I would say that within science, you must always work within scientific logic. be daft and have things that break rules that we know do apply, but be creative, have a whole approach that's creative. The important thing is, though, that people that are adapters, when they look across at the people in their organization who is an innovator, they see a perceived behavior. They see somebody who's an innovator who likes to change the rules and turn things upside down as unsound, impractical, risky, abrasive, threatening the established system, causing dissonance, possibly glamorous, possibly exciting, but possibly also dangerous. And when the innovator looks the other way at the adapter, the perceived behavior is that they are sound, sure, safe, predictable, inflexible, wedded to the system, intolerant of ambiguity, and probably boring. And this is a tense misunderstanding waiting to happen. And sure enough, that was what I was finding, that with me as an innovator, my bosses tended to be adapters. And although we generally got on, it sometimes ended up with a complete misunderstanding. Now, what's this got to do with teams? Well, the fact is that if you want to have a team that has to discover a new technology, something that needs to be radical, for example, a different way to approach COPD, you give it to, the COPD, as we talked about earlier, you give it to a team who are at the innovator end, and they come up with something different. And that's what happened in the company. But that has to go to market. That has to go through stages of development. And what you don't want to do is to have all of your innovators moving through and trying to make it through to the market. You need to change the team. You need these precious people in the middle who can start to wean it away from the innovators who will always keep innovating and changing the rules as it goes through. You freeze it, you get a design freeze, and you don't let anybody reinvent around it. And as you move forward through to the market, then you want people to be adapters. And your adapters are the people in the regulatory department. And thank goodness they're there. Thank goodness they're adapters. And in marketing as well. So when setting up teams to do research and development and have creative ideas, we need to be aware of the differences in personality, how they see each other, manage the way they work with each other, accept the differences, but structure the team so that you get the best creativity, you get the best transition and technical transfer, you get the best regulatory and the best clinical trials. You don't want innovators doing clinical trials either. Now, for me, that was really a transformational experience to get behind it and understand it. And I'm pleased to say that although Curtin himself, Michael Curtin, who is a remarkable character, a psychologist, and his life story is really interesting, but there is still the CHI Foundation. And the CHI Foundation is KAI, Kirsten Adapter Innovator Foundation. And their logo is find out more about your problem-solving style and why it's important. I'm quoting from their website. Plus the importance in understanding thinking style in the context of cognitive diversity, leadership, and effectiveness. So I would advise anybody who's wanting to lead teams of discovery, leading through to product launch, anybody in this industry who wants to be effective in teams, to think about the CHI, KAI Foundation and the way they work.
Yeah, that all rings very true to me, Paul. I just can remember always having the issue of making sure we had the innovative people who are making changes, making inventions. And I can recall we defined the start of true development as the point at which we don't need any new inventions, because we have to freeze everything. And that then has to be an unchanging product that goes all the way through to the marketplace. And innovators can't do that. It makes them crazy. You know?
That is just perfect. I think that's a lovely way to to finish the discussion.
Excellent.
Paul, thank you for those tremendous insights. I'm sure our audience will find it very useful as they work to set up product development teams to bring their new innovations to market.
I have one question. It might initially sound like it's off the wall, but I'm just curious. All right. You were there in Britain where chromatography was invented. And there were two key scientists that did that won the Nobel Prize. Archer John Porter Martin and Richard Lawrence Millington Synge. So I just wondered, was there a direct linkage between the kind of things you were doing with Unilever that went back to that invention of chromatography?
Yes, chromatography is clearly important because, in a way, a lot of people refer to lateral flow as immunochromatography. I don't think it is actually immunochromatography, but it's a fair way to describe it. And my first thoughts about this, even before we'd heard of nitrocellulose wicks, was to try and see if I could couple antibodies onto chromatography paper and make a kind of zone of capture and run an enzyme immunoassay down the strip. It was very crude. It didn't work because there were horrendous problems of background binding. And I tried it a few times and gave up. It wasn't until Mick Pryor and Keith May came on the scene and they were able to introduce the benefits of nitrocellulose and have different ways of thinking and being consummate at making the prototypes work. I completely forgot about the paper until recently when I'm thinking about paper again. And in that sense, the chromatography and the idea of just separating out proteins on a flat lateral flow surface really was a predecessor, although I think probably we weren't quite aware of it at the time. So yes, that's a good question. And if we hadn't got those materials available to make us think that way, maybe we wouldn't have come up with it.
Fascinating. Well, I think we've gotten through everything and more. It's just been wonderful. A lot of fun. Glad you had a chance to tell us about so many things.
I really enjoyed it. I've enjoyed this. I enjoyed the preparation for it. It's a timely thing to do. Couldn't have come at a better time.
That's wonderful.
Glad to hear that, Paul. Thank you so much, and best of luck in your retirement when that comes.
Well, thank you very much. I really am honoured to take part. I'm absolutely delighted.
Well, we're honored as well. Thank you so much.
Thank you, Paul.
Thanks very much for listening to Season 2 of Halteres Presents. We look forward to bringing Season 3 to you soon.
Thank you for listening, and we'll see you next season.
Halteres Presents is produced by Halteres Associates, a US-based bioscience consultancy that provides strategic and tactical services in the areas of diagnostics, medical devices, and life science research to clients of all sizes. The views, information, or opinions expressed during the episode are solely those of the individuals involved, and Halteres Associates is not responsible for any errors or omissions or for the results obtained from the use of this information. The information provided in this episode is for informational or educational purposes only and is not intended or implied to be a substitute for professional medical advice, diagnosis, or treatment. Halteres Associates would like to say thank you to this episode's guest or guests, and thank you for listening to this episode of Halteres Presents.